Not yet. Still 5 minutes.
Okay. So our first speaker in the academic year in our seminar is Paweł Nurowski from the Center of Theoretical Physics and Guangdong Technion. Can you tell us about Beltrami in the system?
Thank you very much. I am very happy to be here. And today I would like to tell you something about essentially the Sitter space. What I really want to do, I want to make an advertisement for a paper that I wrote and nobody reads it. And the paper has almost the same title, but it has extended title. So the title of the paper is the Beltrami de Sitter model, and then there is Penrose's CCC, Radon transform, and exceptional simple Lie group G2. So that's the title of the paper. Today I will not tell you everything which is in the paper, but I will tell you two things. The first thing I will give you a way of seeing the Sitter space. That's number one, like a geometric way of seeing the Sitter space. And number two, I want to show that there is some mysterious connection between the Sitter space and simple exceptional Lie group G2, which is the smallest of exceptional Lie groups. It has dimension 14. So that's the plan. And so here the talk will have three parts. The first part will be about 2 dimensions, because we understand that everything in 2 dimensions, that will be just straightforward generalization to any dimension. The second part, it will be about how to relate the Sitter and Beltrami space, which is another space, to split real form of the simple exceptional Lie group G2. And eventually, I will show you how to generalize everything which I said in 2 dimensions to any dimension greater than equal to. Okay, so my first part is just like how to view the Sitter space. And this point of view, I learned it from a friend, Mexican friend, Gil Bor. He told me this. And I would like to show you this because it's actually a very beautiful thing. So imagine that you have a 2-dimensional plane. Simply take R2, and from this R2, remove a disk. So think about R2 with a disk, this blue thing removed. So on this complement in R2 of this disk, I claim that there is a natural conformal structure. And this conformal structure is defined very easily. If you have to define a conformal structure in a manifold, you have to see what are the light cones. And you define light cones as cones that are tangent to the disk. Okay? So if you have a point here, a light cone coming out from this point is just a cone made by 2 tangents to the disk coming from this point. Okay, so so you have just like this R2 with the disk removed, and if you have a point, a light cone from this point is just a cone that is tangent to the disk. Okay, and at every point you have a light cone. Okay, so this defines a conformal structure, and let's look how this conformal structure looks like. Okay, so I call this space R2 with the disk removed as M2, and as I said, I declare a conformal structure in this, that the light cones in M2 are the cones whose tips lie in M2 and whose generators are pairs of straight lines passing through the tip and tangent to the disk. So one can now look what is the explicit formula for this conformal metric. It's actually very easy geometry. So I want to see what is a null vector here. So this null vector will be just the vector PQ, okay? So there is point P with coordinates xy, and there is point Q with coordinates x plus delta x and y plus delta y. And now a simple geometric fact of course is such that, for example, this vector PQ is parallel to vector PR, so we can write this relation here, and other things we can do other observations. For example, that the distance from here to here is 1 because that's 1, so that's the length of the radius. Then we have Pythagorean theorem that this squared plus this squared is that squared. So this one, and eventually we have that the vector PQ is orthogonal to vector or R. And if you just put this condition and just insert all the data, what is P, what is Q, all these distances, then you will get something that this 0, which stays here, is just this, which says that actually this vector PQ is a null vector in the following metric. Okay, so this is how you get conformal structure explicitly in this complement of R2. And as I say, there is simply declaring that these are just the tangents, the light cones are the tangents to the disk. I get a natural conformal structure on this complement. Okay, this conformal structure. So this is the conformal structure defined by these cones, and one can just calculate Gaussian curvature for example, of this metric. It turns out that it has non-constant Gaussian curvature, but if you just like rescale it by this factor, then you'll get an Einstein metric on this complement of the disk. And you can check very easily that if x and y are such that x squared plus y squared is greater than 1, so we are of the disk, this metric has a Lorentzian signature and is nothing but the two-dimensional de Sitter metric. The interesting thing is that this metric, okay, first of all, this metric blows up at the boundary. Okay, so there is de Sitter space. You have a point here. You have light cones. There are time-like curves there, and these time-like curves go until they reach the boundary, and that's the scribe. So in this picture, this circle is nothing but the scribe of the de Sitter metric. But interesting thing is that actually, although the metric blows up on this circle, it's also well defined inside the circle. The only thing is that inside the circle, this metric changes signature. Inside this circle, this metric is Riemannian. Okay, so somehow this Riemannian metric inside the circle, so it's the same formula. If you just check the signature, it turns out that the metric has Lorentzian signature outside the circle, and it has Riemannian signature inside the circle. So on the boundary, it changes signature. So it is degenerate on the boundary. It's some eigenvector, some eigenvalue is 0, but when passing back, it's just positive, and you get Riemannian signature. This disk with this metric. So if we only consider a disk with this metric, then this metric is something which is called the Beltrami metric on the disk, and it's yet another way of describing non-Euclidean geometry on the disk, different than the Klein model. In the Klein model, the geodesics are circles, parts of the circle starting and ending at the boundary. Here, in this metric, The geodesics are cores of the disk. So if you have 2 points in the disk, the geodesic passing through these 2 points is just a straight line, which is just a chord of the disk passing through this switch. So it's yet another model of non-Euclidean geometry, complementary to this one that is given by Poincaré model. Sorry. Okay. So as I said, in particular, the geodesics in this metric connecting any 2 points in the disk are chords of the disk passing through these points. Okay. So
just a simple question: is it possible to turn it upside down?
Yes.
In the sense that
yes. This is in the paper. This is why you should read my paper. I told you that this talk is about main advertisement of my paper. All your questions are answered in the paper. The paper is 50 pages. Nobody reads it. So I'm just doing it, the advertisement for you. Yes, you can do it. Yes.
That's all similar. Differentiation is observable there's an observable in the inside of the metric, and if you flip it out, you still keep the
Read the paper. It's explained there. Okay. I have a lot to say, so it's why I have to cut off stuff. Okay. But it's a very neat model how to view the Sitter space. The Sitter space is outside the ball, outside the disk. The boundary of the disk is just scribe, and inside there is Riemannian metric. Okay. Okay. As I said, I learned it from Gilbert, and I praise him once again because I really learned it from the guy in Mexico. Okay. Okay. So now let me pass to something more exciting, namely. So somehow I have a hybrid. I have a hybrid of Lorentzian Riemannian manifold. Entire R2 is here Lorentzian, inside Riemannian, and on the disk it changes signature. And you can think, what are the geodesics in both metrics? So for example, outside the disk, the story is Lorentzian, so there should be null geodesics, there should be time-like geodesics, and there should be space-like geodesics. So we know what are null geodesics. Null geodesics are Euclidean straight lines in R2, tangent to the circle. So these are this yellow thing, if you see the color yellow here, right? So these are the null geodesics. So null geodesics are Euclidean lines in R2, tangent to the circle. What are the time-like geodesics? Time-like geodesics are these red lines. So these are Euclidean lines starting somewhere in infinity and approaching the scribe. Okay? So these are the red lines. So those lines that don't have, as I said, the null geodesics are straight lines tangent to the disk. The time-like geodesics are straight lines secant to the disk. And the space-like geodesics are straight lines that do not intersect with the disk. These are the green lines. Okay? So this is a very nice model because the geodesics are just Euclidean lines. Right.
So they intersect twice.
Yeah, so you should understand. So that's okay. So if you want to, because that's my view on Penrose CCC, but the Penrose CCC should be Lorentzian here and Riemannian here. Penrose says that it should be Lorentzian here. Why? It is there's a natural one which gives Lorentzian to Riemannian. Okay, so the story is here like this: that there is this guy here, and he goes on a geodesic in infinite time. He reaches scribe, but after, very smoothly, he still goes. But now he's Riemannian guy, and he goes, and he goes up, and he becomes Lorentzian again. I have a lot. Read the paper. All of this is in the paper, but I have other things to say. Okay, so let me, as I said, the paper has 3 subtitles. The first one, Penrose's CCC, and this will be not in this lecture. Okay, so now in this lecture, I want to. Okay, so inside, as I say, inside the disk, there are these brown chords, and these are the geodesics inside the disk. So somehow, what I want to say is that actually, although the geometry, something is going on with the geometry, the signature of the metric changes, but there is absolutely smooth passage here. There are geodesics which are just defined everywhere. You know? Okay, so that's what I wanted to say. Okay, so now I want to tell you something more interesting. Namely, I claim that everything what I said is projectively invariant. And there is something which is, again, very well-known subject in 19th century, and it's something which is called duality between points and lines. Okay, so let me discuss this. So I claim that every point outside defines a straight line inside. So to every point here, they correspond a geodesic in the Beltrami space. So this is the sitter, this is Beltrami. Every point here defines a chord by this simple geometry. So to every point there exists a line inside. Okay, as I said. So I call, if I call this point P, I call this line CP. That's me. But I will ignore it. Okay, so that's this point defines point P defines a line point in the theta space define a line in the Beltrami space. Okay, I call this line CP. Okay, so that's. But as I want to say, I want to stress that also the opposite is true. Every point here defines a line outside the disk. So in other words, a point inside defines a space-like line outside. And this is something that I think that also Gilbert told me this, but then I found it in a book of William Thurston, the very famous book on three-dimensional manifolds. This picture, okay, my picture is more beautiful, but that's essentially the picture from the book of Thurston, and it essentially tells you how to point here as assign the line. If you don't understand this picture, watch this, which I just animation made by ChatGPT for me. I asked ChatGPT to make animation. Let's do it. Where is this? Oh, let's start again. Sorry. Okay. So I have a green point inside, and I'm now just moving chords around this point. And magic is magic. And what you get after this, like rotating the chord along the point, produces, as you see, a beautiful line, right? So there is like, to every point here, there is a line outside, okay? So this is a good story. So we have this hybrid of Lorentzian Riemannian manifold. Every point here define a geodesic here, and every point here define a space like geodesic there. Okay. Okay. This is we are in dangerous situation because there should be some other movie coming on, and this would be bad. Okay. Now, okay. So, are you with me? We have duality between points and lines. Points and lines. Good. So I will now consider pairs of points. A point outside and point inside. Okay. So consider a pair of points. Point P, little p of a point in the de Sitter, and point capital P inside the disk, right? So, as I said, small p is M2, and capital P is in B2. Okay, so now I have a pair of these things. And to distinguish between points outside in M2 and inside in B2, I use letters from the end of the Latin alphabet to coordinate points in M2. So, for example, point P in M2 will be denoted with letters X and Y, and point capital P in B2 will be denoted by letters A and B. Okay. Okay. So now there is we have this duality, as you remember. A point here defines a line here, and point here defines a line here. Okay. Good. So now I can use this funny thing to transform fields from the Lorentzian regime to the Riemannian regime, and from Riemannian regime to the Lorentzian. Oh, that's something which is called a Funk-Radon transform, and let's do it. So I say that if I have an integrable function in the de Sitter space, so here in the white field, so if I have a function f in the de Sitter space, and suppose that it's integrable, define a function f hat in here in the following way, that value of this function f hat in a point AB will be value of the function f integrated over the line corresponding to B. Simple as that. Value of a function in point FB, take function f in here, integrate it over the line corresponding to AB, you will get a function at AB. So you will have a function in here. Do you agree? If I have a function, yes. Standard measure type. Yes. And I can do the other way around. So in a way, if I have a function here, as I said, in here, then I define a function in here by assigning value at the point of B of this function f star to be integral of this function f along the line corresponds to the point at B. And likewise, the other way around. Given a function in the Beltrami space, I define a function in the de Sitter space by integrating, so the value of this function f at the point xy here will be value of the function f integrated over a line corresponding to this thing. And this way I can just transform something from Lorentzian thing to the Riemannian thing. I do it for functions, I can do it for tensor fields or whatever I want. Okay. So let me summarize. Given a function in de Sitter, define its value in some point AB in the Beltrami as an integral in M over the line corresponding to a point. And likewise, given a function in Beltrami, define a function at de Sitter at point xy as an integral in B2 over the chord corresponding to point xy. Okay. So this gives, as I say, this gives a modular Funk-Radon transform between functions in M2 and B2. And somehow, contrary to a very coordinate-dependent Wick rotation that transforms fields from Lorentzian to Riemannian thing, this is geometric. It's very geometric transform. It's a very geometric transform. So that's the first message, that you can use this gadget to transform fields from Euclidean to Riemannian regime and the other way around. Okay? Okay. So now what I do, if this idea of having point in here and in here was kind of successful to transform the fields, so why not to consider the space, the four-dimensional space of these pairs? Okay. So I now consider a space T, which is Cartesian product of this M2 and B2. And it's a four-dimensional space. So I restrict that X and Y is in the de Sitter and A and B is in the Beltrami, right? And I call this space correspondence space for the two-dimensional Beltrami de Sitter model. And what I show now is that this four-dimensional space also has a natural conformal structure. It has a very natural conformal structure, although you will see that it's just a bit tricky. So as I said, I will show now that this correspondence space has a natural conformal structure. Okay. So how do I do this? Okay. If I have a point outside in the sitter, so suppose that I have a curve here, that the point is moving. Okay. So if point is moving from P to delta P, it's the chord corresponding to small p changes to chords corresponding to P plus delta P. So these chords will intersect. And here there is hidden treasure. They will intersect inside, provided that this movement of this point is along a space-like curve. So if this point moves along a space-like curve, the intersection here, from going from point to point, will always be inside. So in this way, to a curve here, I have a ghost curve here. So there's a guy going in the sitter on a space-like curve. There is another guy, his ghost, in Riemannian regime, going there. So I call this guy ghost. Okay. So there is a ghost. As I said, that's the story. Okay. The other way around. If I have a point in here, and if capital P now going to P plus delta P, the same. The lines here will now intersect without any restriction. If these guys are here, they will always produce the space-like line. And therefore, to a curve here, there is a curve here, a ghost curve there. Okay. So as I said, we have ghosts here. So I can even calculate explicitly, if I have this P plus delta P, I can see how the P, capital P with small index P looks like, or if I have capital P, I can see how this small p with capital P index looks like, right? And in my coordinates, you can calculate this thing. So to a curve P of T here, which is space-like, they're corresponding a curve P with capital P with small index P of T in here. Likewise, to a curve P of T here, there corresponds a curve small p with the index capital P here. Okay? So you see that for this thing, if this curve is moved, so this curve must move to see something non-trivial here, you see? Okay. So now this defines, this enables to define kind of choreographic movement of a pair of curves. So suppose that now I have a curve in my correspondence space. So I have a curve in correspondence space, maybe P of T, comma, capital P of T. So I have a curve of this. And I say that these two curves are moving in some coordinate movement, provided that, I call it dance, they are dancing. So this guy here dances with that one, provided that this guy at every moment goes toward the ghost of this guy. And this guy at every moment goes towards the ghost of that one. You understand what I said? We say that a pair of these points dances if the point small p moves in M2 in the direction of the image of the ghost of the point capital P, and the other way around. Okay? This is sort of a ghost dance, because if the guy here doesn't know the guy there, because this guy lives in a different space. This is in Lorentzian space, this is in Riemannian space. But corresponding to this guy, there is a Lorentzian guy, which is his ghost, and this guy can see it, and he can go towards it. Likewise, this guy cannot see that guy. The guy inside cannot see the guy outside, but it can see its ghost, and he can go at every moment, go in the direction of this. So it's like a coordinate movement. So I ask them, listen, two guys. go in such a way that you go towards the ghost at every moment, goes to the ghost of the other guy, and so on. Okay. That's what I want. Yeah, so that's what I said. We have a point here, and it's ghost, so we have a pair, P and P. Corresponding to this guy, there is this ghost, and corresponding to this guy is this ghost. So it's natural to us that this guy at every moment goes in the direction of that, and this guy at every moment goes in the direction of that. Some strange idea, but I say that this pair will be dancing if they do this. Okay, so what does it mean? Okay, that's what I want, right? That's what I want to do. Okay. So one can calculate what this dancing condition means. So I take a curve in my T, in my correspondence space. So there is this one curve outside and one curve inside. And my dancing condition means that the velocity of this guy, so namely this thing, velocity of the point P of t, which is point x of t, y of t, should be in the direction of the line between P of t and the ghost of the other guy. And if I write down these conditions, I get something like this. I get two conditions, like this or like this. So that's a parallel of the velocity to the line, parallel of this velocity to this line. And if I just, for example, from this equation eliminate lambda, then I will get something. I will get this. Or if I eliminate from this condition mu, I get the same. So these two conditions define this. So infinitesimally, this dancing condition means that point x, y, a, b, when moving to point x plus delta x, y plus delta y, a plus delta a, b plus delta b, should be such that they satisfy this. And what you see here is just a quadratic homogeneous condition in the a, the x, and y, the b. So this means, essentially, that my dancing conditions means nothing else but that the pair of these curves, which is a curve in my T, is nothing but null curve in such metric. So the dancing condition I defined for this P of t and this P of t in the language of the correspondence space means that this curve is nothing but a null curve in such metric. And now we can see that this metric is strange. First of all, it's conformal because the only thing I require is just that this is 0. So actually, there is a conformal metric defined on this correspondence space. And if you just look at this metric is of signature plus minus plus minus. So it's split signature metric. It's conformal metric of signature plus plus minus minus. I just created everything from thin air. I started with a disk. And now I have a conformal metric in 4 dimensions with split signature. This metric is quite an interesting metric. It is solely defined by the projective structure of R2, because the only notions I used in creating it were notions of points, lines, and incidence conditions of point lying on a line or point tangent to the line or line intersecting. They are all projectively invariant conditions. So this conformal structure is actually projective. And actually there is a conformal structure, and because it is PGL3 symmetric, so this conformal metric has at least symmetry of SL3R, local symmetry of SL3R, which, good to know, is 8-dimensional. This Lie group is 8-dimensional. So this thing, this metric on this correspondence space of Beltrami de Sitter model has an 8-dimensional, at least 8-dimensional, the algebra of symmetries. Okay, a good one. Moreover, this metric can be made into Einstein metric again by choosing appropriate scale, and actually you can choose the scale for which this metric is Einstein. And actually it is very nice Einstein because it's just like self-dual Einstein. It's not conformally flat, it is self-dual Einstein. And the dancing pairs are nothing but null curves in this conformal in the conformal class of this metric. And the conformal class, as I said, has the Lie algebra SL3 R as its full algebra of conformal symmetry. One can say that actually the full algebra of conformal symmetry is actually SL3 R. And these conformal symmetries of the conformal thing are actually killing symmetries of this metric. Okay? And it turns out that this metric is locally isometric to something, to a split signature version of something which is called Fubini-Studi metric, which is projectively invariant, but Fubini-Studi is of Riemannian signature. Okay? Oof. So let me conclude the part one of my talk. The Sitter metric, so I'm just repeating. I just started from nothing, from a disk in R2. And then I saw that complement of this disk is nothing but the Sitter space. And this metric naturally extends inside the disk, where it has this Beltrami metric inside. And this thing, in turn, defines this correspondence space of Cartesian product of this what is outside the disk, this what is inside the disk. And this, in turn, is equipped with an Einstein split signature metric with precisely 8 conformal killing symmetries. Okay, quite a thing. I created it from nothing with the help of Gilmore, no doubt. I wouldn't do this if Gilmore didn't tell me some parts of it. Okay, so now what is the relation of the split real form of exceptional regroup G2? Maybe in this seminar I have to say something about geometry of distributions because people don't know it, maybe. When I was a student, I knew it, but I don't know. Now, people don't know what it is a vector distribution. Okay, so rank K vector distribution D on a d-dimensional manifold M is a smooth map from which assigns to every point P in M a k-dimensional subspace in the tangent space. Okay, so that's what distribution is. And such distributions can be defined in terms of k nowhere vanishing vector fields, which are just like linearly independent at each point, and a distribution then is just like span over functions, so it is like a module over functions on M of these vector fields. Okay, so that's what distribution could be. And the next thing is, I say the minimal notions about the things of the distribution. We say that a vector field is in the distribution if its tangent vector at the point is in the plane, in this K plane dp. Okay, and now given a distribution D, we can now get a new distribution, which is just span of all commutators of the vector fields being in the distribution. And this I call D1. So this is again distribution. If the distribution D is integrable, it is just nothing but D. But if the distribution is non-integrable, it's something bigger than D. Okay, and likewise, I can now define D2 as a span of all commutators of vectors from D and from D1, and that will be calling D2. And it may be D1, but in general, it is something bigger. And then you have a sequence, given a D, you have a sequence of distribution. You start with a distribution that is bigger one, unless this is integrable, it stops, but if it's not, there is bigger one, and there is some, it cannot be bigger than the tangent space. So eventually it is bounded from above by the tangent space, right? So I assume that each such distribution, di, has a constant rank. Okay, so it is a distribution in my sense. So associated to a distribution D, you have a such vector of non-decreasing integers, which are just the ranks of D, ranks of D1, ranks of D2, and eventually one or last of them may be integrable, so it has rank of this integrable one, or if it is non-integrable, the last would be just dimension D of the tangent space. Okay. As I say, of course, integrable distributions are such that this KR is K, so it stops here. But if it's non-integrable, it can just go, and it grows. Okay? This thing is called growth vector, and is the simplest diffeomorphism invariant of a distribution, such vector. Okay? So that's a primer on distributions. I need it, and now it turns out that the most interesting for me and for various people are something which are called 2, 3, 5 distributions. So there are such distributions in dimension 5, which are just rank 2. The D1 has rank 3, and D2 is already the tangent space. Okay, so according to Cartan, such distribution that is 2, 3, 5 having rank 2, D1 having rank 3, and D2 having rank 5, these are generic distributions among all rank 2 distributions in dimension 5. And they are very interesting because it is the first dimension in which the distributions have different invariants than this growth vector. So actually there are plenty of invariants for such distributions. And actually, Cartan found all of these invariants for these 2, 3, 5 distributions. So if they have invariants, so it means that 2, 3, 5 distributions, so meaning generic rank 2 distributions in dimension 5, they can be split on locally non-equivalent classes with respect to diffeomorphism. Okay? So they split onto non-equivalent classes under local diffeomorphism. In the particular, there are locally diffeomorphically non-equivalent homogeneous distributions. So even if 2, 3, 5 distributions have symmetry, there could be such that are locally non-equivalent. Okay, among locally homogeneous 2, 3, 5 distributions, there is the most symmetric one. So there's this entire realm of 2, 3, 5 distributions. Some of them may have no symmetry, some of them have symmetries, but there is the most symmetric one. And this most symmetric one among 2, 3, 5 has, and is the result of Cartan of 1890 or 80 or 90 or something, 1889, let's say. The result of Cartan is that the most symmetric of these 2, 3, 5 distributions has split real form of the exceptionally simple Lie group G2 as its symmetry. So actually the first realization of a exceptional Lie group G2 was realized by Cartan as a symmetry of a certain rank 2 distribution in dimension 5. Okay, okay. So let me. So as I said, among all of these 2, 3, 5 distributions, there is a one which is locally equivalent to the most symmetric one, and this most symmetric one has G2 as the group of symmetries. This is a 4-dimensional simple Lie group, and is of the classification neither A, neither B, nor C, nor D, but G and 2. Okay? Okay. So it turns out that if a 2, 3, 5 distribution, 2, 3, 5 distribution may have no symmetries, or it have some symmetries. But it turns out that if a 2, 3, 5 distribution, if you are able to show that the 2, 3, 5 distribution have 8 symmetries or more, it means that it have 14. Okay? So there are distributions, 2, 3, 5 distributions with strictly 7-dimensional group of symmetry. But if it happens that you find a 2, 3, 5 distribution with 8-dimensional group of symmetry, actually it has 14-dimensional group of symmetry and it is G2. Okay, that's a result of Cartan as well. So according to Cartan, whenever you meet 2, 3, 5 distribution, just check its symmetry. If you find 8, it means that it has G2 symmetry. And there is a zoo of these 2, 3, 5 distributions. It's a huge zoo. Okay, so now there is a theorem which we made with Daniel An some years ago. So let me quote the theorem. So every four-dimensional manifold equipped with a split signature metric defines a five-dimensional manifold. So every four-dimensional split signature metric manifold defines a five-dimensional manifold, which is a bundle of totally null two planes over this manifold. So as I said, every four-dimensional manifold TG equipped with split signature metric G defines a five-dimensional manifold T, which is its bundle of all real totally null planes of a given self-duality. So in other words, we have given a T with split signature metric, four-dimensional with split signature metric, we have a five-dimensional one, which is a fiber bundle over this with a fiber being a circle or SO2 group. Okay? So this bundle T is actually, this one, is actually defined solely by the conformal structure of this split signature metric. So because the only thing I use to define it are just totally null planes. So nullity place. So as I said, this bundle T only defines is depending on conformal structure of the split signature metric, and this five-dimensional manifold associated with this conformal TG is canonically equipped with rank 2 distribution. It's a magic, but it is. So if you give me a four-dimensional split signature manifold, four-dimensional manifold with split signature metric, there is a unique rank 2 distribution defined on this naturally defined bundle T. And this 2 distribution is 2, 3, 5 almost everywhere. And it is 2, 3, 5 provided that the Weyl tensor of the four-dimensional conformal structure has non-vanishing its self-dual part. Okay? And this distribution D is called twistor distribution of this conformal structure TG. Okay? So now let's combine everything together. Remember, there was de Sitter, then there was Beltrami, there was Beltrami de Sitter, there was correspondence space. This correspondence space was four-dimensional conformal split signature. So it has this twistor bundle, it has this bundle T, and it has natural 2, 3, 5 distribution because the metric is, as I said, self-dual. So the self-dual part of the Weyl tensor is non-zero. So there is a natural 2, 3, 5 distribution associated with this de Sitter space or Beltrami de Sitter space. So if I have 2, 3, 5 distribution, I have to check what is its symmetry. But as I said, everything is natural here. To define this distribution D, I need only conformal structure. So, but the conformal structure of my dancing metric, conformal structure of my dancing metric, has 8 conformal symmetries. But now I define a distribution using only the conformal notion. So this distribution should have at least 8 symmetries. But if a 2, 3, 5 distribution has 8 symmetries, it has G2 symmetry. So there is a natural G2 symmetric distribution associated with the Sitter space. Like I started with a disk, you know? Okay, that's what I just said. As I said, take the correspondence space, go to the bundle. It's almost everywhere 2, 3, 5. Since the twistor distribution is canonically defined by the conformal structure, the conformal kinnick symmetries leave 2 symmetries of the twistor distribution, but the dancing metric has 8. But if 8, it means that that the distribution has G2 symmetry. Okay, so interesting. It's something like this. So conclusion of part 2: the Sitter space in dimension 2 canonically defines a split signature conformal class in 4 dimensions, which has split G2 symmetric twistor distribution. Well, okay. So that's part 2. Part 3. Can I do it in any dimension? Yes, I can. With some sweat, okay? So everything I said about the Sitter space in dimension 2 easily generalized to any dimension. this in particular includes the existence of the dancing metric. And now the dancing metric has split signature DD. Okay? The interesting story is how to associate the split G2 from the Sitter space when D is greater than 2. So what I know how to do it when D is equal 3. When D is equal 3, meaning if I start with with R3, remove a ball, then I define dancing metric, then I define twistor distribution, twistor space and twistor distribution, and I can show that this somehow has G2 symmetry. I will show you this. And I also know, but really with a lot of sweat, how to do it when dimension is 4, the physical dimension. So in the dimension 4, I also can associate G2 to the de Sitter space. If it is possible for higher dimensions, this I don't know. Okay, I could stop here, but I can see if I still have 1 minute, then I can tell you how to do it. So this is a short message, and I made a short message to finish. But if you are not bored, some of you are, but I don't care. Then we go further. So now let me see how I do this thing in the details. So now instead of the disk B2, we remove a ball B of dimension D of radius 1, centered in RD, obtaining MD, and this gets a conformal Lorentzian structure in the same way. You have a ball removed from RD, and then consider the cones tangent to this ball. And this will produce a conformal structure outside, and it's nothing but the Sitter space. So for example, this is how you should see, it is how you should view, in my opinion, conformal compactification of the Sitter space. The Sitter space in 4 dimensions is just like a 4-dimensional ball removed for R4, and the Sitter space is just everything which is outside the ball. This what is the boundary of this ball is just a scribe. Okay, so that's the first thing. So I can just even write explicit formula for this thing in any dimension. And again, this metric is Lorentzian outside, but it's Riemannian inside. So again, we have Lorentzian-Riemannian hybrid in RD, which is just gluing conformally the Sitter with Beltrami inside. Okay, so this is easy. As before, we also have the correspondence space, the same story. And on this correspondence space, we even have the dancing metric. Even if you are interested, I can show you how to do it geometrically, but you can, that's the formula for this metric. Okay, so you have the dancing metric. Now the twistor bundle, so this bundle of real totally null planes, these planes should now have dimension D. So this bundle is now SOD. Before it was SO2 bundle, circle bundle over T. Now it is SOD bundle over T. The twistor distribution now has rank D. So now we have a twistor distribution in the twistor space. And here the difference between D equal 2 and D equal 3 starts to play, and you see that it's just like tricky what's going on now. Because I would like to have that this distribution has G2 symmetry, but it doesn't. It doesn't, but it has something better. It has something actually more weird. So because now the rank of the distribution is greater than 2, so it cannot be 2, 3, 5, because 2 is just from rank D, and rank D is greater than 2. So if for D equal 3, it will be 3 something. So let's see. And moreover, so for D equal 3, it will be rank 3 distribution. And now the bundle T now will have dimension 3 plus 6, 9. So it will be rank 3 distribution in dimension 9. Rank 3 distribution in dimension 9. Now you can play the game. You can just like commute and get D1, D2, blah, blah, blah. But the bad story is that there is no theory of 3 distributions in dimension 9. So you have to, but we have a particular example, so I can do something with this. So let me tell you what's going on here. So as I said, no invariance theory known of such distributions. So in principle, I can make this theory, but I don't care because I have my simple story. So I have my now rank 3 distribution in dimension 9. And the first thing is to calculate the growth vector. The funny thing is that the growth vector is free, then it goes, D1 is of rank 4, then this goes to rank 6, and this rank 6 distribution, which is D2, is integrable. So there's 3, 4, 6, and then there's foliation of this 9-dimensional space by these 6-dimensional leaves of this D3 distribution. Okay, so as I said, to my big surprise, the second derived distribution is integrable. It's a big surprise for me, but a further surprise is that on every 6-dimensional leaf of this D2, the twistor distribution is very special because it has something which is called Cauchy characteristic. Cauchy characteristic is a certain symmetry, is a symmetry of a distribution lying in the distribution. That's what Cauchy characteristic is. So that I have my free distribution. So now I restrict everything to one leaf. One leaf is 6-dimensional, and I have 3, 4, 6 distribution there. This 3, 4, 6, this free distribution has a Cauchy characteristic, meaning a symmetry along the distribution. So if I have something like this, so let me summarize. So now, the 9-dimensional twistor bundle is foliated by 6-dimensional leaves. The distribution D of rank 3, D1 of rank 4, and D2 of rank 6 are tangent to every leaf Q. Thus, on each leaf Q, I have 3, 4, 6 twistor distribution, equipped with a 1-dimensional symmetry given by the Cauchy characteristic. Let us denote this symmetry by X. So now I can divide Q, which is 6-dimensional, by the symmetry of the distribution. Then I will get a 5-dimensional manifold, and this will go to 3, 5 distribution on the quotient. And if I have a 5-dimensional manifold and a 3, 5 distribution, I check the symmetry, and the symmetry is G2. So it is how you associate G2 symmetry with 3-dimensional de Sitter space. As you see, it's very different than before. And you might say, does it continue? So I say that I know how to continue to dimension 4, which is still very different than this what you saw, but there is still a possibility of associating G2 with 4-dimensional de Sitter, the physical one. If it goes, what's going on beyond 4, I don't know. Okay, so as I said, this talk is an advertisement for the paper. There's much more, because I especially removed the CCC part, which is subject of this seminar, but you cannot sell refrigerators to people in the Arctic. As well, you cannot sell sand to people in Sahara, but you can sell refrigerators to people in Sahara and sand to people in the Arctic, right? So it is why I was just not telling about physics here. Thank you very much.
May I ask a question first? So my question, the question is that your starting point is, let's stick to 2-dimensional for simplicity. Your starting point is R2. Now, if you replace R2 with any other manifold, I mean, remaining manifold, then what's happened? I mean, all the construction should go through, right? And do we know what's going to happen then?
No, and that was also my question. Can I deform it? And can I deform it? So that would be bad. And as far as time passes, I cannot deform it so far. I think it's rigid. I think that this story is really rigid. So only there are these flat models.
So, for example, if you start with kind of Euclidean 2-dimensional decision, then you can define a circle, then you can define.
Yeah, I understand. You can define a geodesic ball. And you can do in MD. So if you have MD with a Riemannian metric, you can define a geodesic ball. Remove the balls, take the Riemannian geodesics to define a tangent cones, everything goes. But I tried to define because actually I wanted to make some nice model of because my main thing is that motivation for this thing was definitely Roger Penrose and his conformal cyclic cosmology. That was the motivation. And then I observed that actually he wants that universe, which is the center at the end, as we believe now, at the end of the evolution of the universe is the center. So we have the center here. And Roger wants that beyond there will be perhaps another de Sitter, still Lorentzian, right? But I said it's crazy because actually de Sitter naturally, conformally, prolongs to the Riemannian guy, to the Beltrami. And it's just like God given. You don't need to do anything. It's there. The geodesics, the Euclidean geodesics go from Lorentzian to Riemannian thing without any trouble. They are just smooth as they can be. You cannot glue anything. You cannot do any artificial thing. That was my motivation, and of course I wanted to deform it, but I did. And if your question is a question that I also ask myself, but I don't know how to do it yet. Or maybe I'm too lazy. Because there is another thing I dare to say. So let me say it is relatively the same. So we can say whatever we can say. So I believe that this universe is full of such Riemannian blobs. The dark matter are these Riemannian blobs. The light cannot go to there, or it goes, but infinite time from this side and this side. We have full of these guys, these Riemannian blobs. So our Lorentzian thing is just like a pie with raisins stuffed with these Riemannian blobs. That's the ultimate thing I could say.